In this lesson, we are introducing radioactivity. Our lesson objectives determine what makes an atom radioactive and compare and contrast nuclear particles in terms of their mass charge and penetrating power. So if we look at an example like uranium, how can we put 92 positive charges into a tiny volume without these particles flying apart due to the repulsive nature of these like-charged protons? Well, there exists a very strong attractive force between the protons and neutrons, which is called a strong nuclear force. And when they get really close together, it has the ability to hold the nucleus together. But what happens is this force only works over short distances. So as the nucleus gets larger in terms of increasing the number of protons and neutrons for larger atoms, the electrostatic repulsion between the protons increases faster than the strong attractive force holding them together. And so some particles then get fired off or shot out, or we can say emitted. And so the process by which a nucleus emits these particles, as it fires them off and changes into new elements, is called radioactive decay. And so when we have a radioactive nucleus, one that's unstable due to those electrostatic repulsive forces, it's going to emit a particle and some energy, and we call this emission radiation. And so when we have radioactive decay, we get what's called transmutation, when this unstable radioactive nucleus decays into a new element. And so how do we make a new element? Well, when we change the number of protons, we change the element. And what happens is, as it gives off these particles, now the electrostatic repulsive forces are minimized. That strong nuclear force can take hold, and the product will be more stable than the reactant. So what types of radioactive decay do we have? And so if you look at table O in our reference table, it gives us a list of types of radioactive decay. The three most common are the first three, which is the alpha, the beta, and the gamma. They give you the notation. In the upper left-hand corner is going to be the mass, and the bottom left-hand corner is going to be the charge, just like the element or the isotope notation that we're familiar with from the periodic table. And they give you a symbol as well. Note that these two particles have for the first three have two different notations. They mean basically the same thing. Here they're just saying that the alpha particle, that's the alpha symbol, is equivalent to a helium atom, and the beta particle here is equivalent to an electron. So you can use either notation. Also recall that we learned about isotopes. Isotopes are atoms of the same element that have the same number of protons, but different number of neutrons, and therefore their mass changes. So if we look at the three isotopes of hydrogen here, hydrogen has one proton. That's why it's considered hydrogen. But these three isotopes have different number of neutrons, and therefore their mass is different. We have no neutrons in hydrogen 1, so the mass is just 1. We have 1 neutron and 1 proton, so the total mass is 2. And then here we have 2 neutrons and a proton, total mass is 3. And here's another example here. We have carbon-12 and carbon-14. These are two different isotopes. Same number of protons, just a different mass number due to the different number of neutrons. And so generally, when the proton to neutron ratio in a nucleus isn't 1-to-1, or at least close to it, we can deem the nucleus being unstable, aka radioactive, due to the repulsive forces of the protons being greater than the binding nuclear force. And so the nucleus will then decay and emit particles over time, and that is our radioactive decay. And so, for example, carbon-12 and carbon-13 are fairly stable and considered not radioactive, where carbon-14 is unstable and radioactive because of the increased number of neutrons and that ratio not being close to 1-to-1. So when you are a smaller element, the ratio of protons and neutrons typically is close to 1-to-1, making it stable, and if it's not, it is radioactive, and we know it can decay emitting particles. All elements that have 83 or more protons, because they're just so large, there's so many protons and neutrons, they are all unstable and all radioactive, and all of those will undergo radioactive decay, emitting particles. So let's check your understanding. Can you determine what makes an atom radioactive? So looking at the first three main types of radioactive particles, the alpha, the beta, and the gamma, if we wanted to separate these particles, what we can do is we can run them through a magnetic field. Because the alpha particles have a charge of +2, they're positive, they're going to get attracted to the negative side. The beta is negative, it gets attracted to the positive side, and then the gamma is going to run straight through undeflected because if you look at the notation here, gamma has no charge, and therefore it's not going to be attracted to either the negative or positive side. Now looking at their ability to penetrate objects, the alpha particles have the least penetrating power. And if you look at the notation, this should make sense. That's because comparatively to beta and gamma, they have the most amount of mass and the most amount of charge, and so they're going to be moving slow and they are much larger. And so we can block alpha particles with paper. Beta particles have greater penetrating power than alpha, and that's because they have no mass, but they do have a charge, and so we can block beta particles with a thick piece of wood. And then the gamma, because there is no mass and no charge, they're just pure energy, they have the greatest amount of penetrating power. And we can block gamma radiation with some thick concrete or lead. And so looking at table O, to remember this, of the first three, it goes in order. Least penetrating power for alpha and most penetrating power for gamma. So now, how do we actually know that radiation is present? How do we measure radioactivity? Well, we can use things like a Geiger counter to measure the amount of radioactivity that's present in a radioactive sample. So the ionizing radiation creates ions, charged particles, and these charged particles then will conduct a current that is measured by the Geiger counter. Another way is to use a film badge. And so a person can either pin on their clothing or wear a badge like this here. And basically what happens is the greater exposure of radiation to the film indicates a greater exposure to radioactivity. So let's check your understanding. Can you compare and contrast nuclear particles in terms of mass, charge, and penetrating power? At this point, you should be able to determine what makes an atom radioactive and compare and contrast nuclear particles in terms of mass, charge, and penetrating power.